at the same speed, what does that tell you? Oh, so close.
What's the question right now?
Yes.
The question right now, so Erica established that Laura had to throw the ball first.
Mm-hmm.
Yeah.
I said, okay, that's the key here. But I said, how do you explain Lou then? The fact that the light from here and here are gonna hit him at the same time. They're gonna travel the same distance, same speed. And it might be just that you're thinking, well, it's obvious that surely I'm not looking for that. But let's just put the nail in the coffin here.
Well, yeah.
So we're trying to figure out what would make one light hit him before the other.
Yeah, why does it hit Lou at the same time, but
The detector at the
detector at,
Because time is different.
Different
for
time.
the detector and blue.
it's not a time issue. Not in the sense of how long it took to get there.
Does it just appear at the same time? It's how fast it's going, but she's on it, so it's not.
No.
Okay.
No. I mean, Erica pretty much said it. And perhaps this has devolved into a mind reading exercise.
Because they're the same distance from her?
They are the same distance from Lou.
That's not it.
One is traveling faster than the other.
Then what you're saying to Einstein is, I don't care what you said. All right, first off, if the two lights flash and they hit Lou at the same time, what does it tell you about the lights going off?
That they're going off at the same time.
Okay. And for Sue, when they are at rest, but the right light hits first, because we know that because it stopped and it was glowing green, what had to be true?
The right light went off first.
Okay. And that is what I was hoping to get towards. The fact that just because two things go off at the same time in one reference frame does not mean that they do it in a different reference frame.
That's what I was trying to
Okay.
say.
I know, and we
That's what I
were,
was trying to say with the frames, Dr. Fox.
oh, sorry.
What?
If I had understood, we would have done 20 minutes
We're
ago.
different. It's okay.
All right, so this is the idea of simultaneity. That things do not happen simultaneously in all reference frames.
Can you spell
Spell simultaneity?
that?
We will find out.
Okay.
I think that's the way simultaneity is spelled. See if I spelled it the same way here. It is the same way I spelled it here.
Well, you spelled it for us, and I still spelled it wrong. Okay.
Like simultaneous, except we dropped that OUS and add IT line.
And it
Possibly.
is that.
Yeah.
That. Can you read, just because something happens. Can you re-say how you said?
Just because something happens simultaneously in one reference frame does not mean it happens simultaneously in another. So let's take a look. That's a classic Cartesian space. Technically, when you're doing relativity, you generally label you'll have an axis, a position axis, and then this typically is a CT axis. I probably won't get into why, but in essence, this is the time axis. So if I have an event happening at this location and at this time, and then I have this event happening in a different location at the exact same time. So I have two events happening at different locations at the exact same time. So any questions about why this graph represents what I just said? As you start getting faster and faster, the axes stop being perpendicular to each other. That you can treat this as you get faster, that the axes will start to, how accurately I can do this. That is horrible. There. So as things start moving faster, basically your, we'll call it X prime and CT prime axes will start to work. Well, if you think about, if I'm at a location here and I want to figure out the position and time, well, when I'm in my classic Cartesian coordinate system, I just travel parallel to the time axis till I get to the x-axis, and that tells me where my position is. If I want to figure out the time, I travel parallel to my x-axis until I hit my time axis, and that tells me the time. We're going to do the same thing here. This event, if I want to figure out what time it happens, well, I travel parallel to my x prime axis, and that tells me the time in the prime frame. This event, so visually, these happen at two different times in the prime frame than they do in the x frame. They happen at the exact same time in the x frame, but this event occurs first in the prime frame. And you can go, it's possible to go through the math and figure out the relationship between that angle right there and how fast you're going. I'm just going to spare you that. So at this point, we've now established that for two objects traveling at different speeds, not only is time not the same for both, but the order in which events happen is not necessarily the same time for both. I do need to point, I feel the need to point out that if lightning strikes a tree, and then I see the tree being struck, there's a time lag there. I see the tree being struck after the tree is actually struck. That is not going to change. That order cannot change. We are not talking about, because of where I'm standing, the order in which I see things can change. We're talking about the order in which things actually happen. And it is not possible for me to see it flash and for me to see it before it actually happens. To do that, we would need to have particles that travel faster than the speed of light. Theorists have, of course, already come up with something, the tachyon. We have no experiment in order to find tachyons. Right now, they will be considered to be just flights of fancy of the theorists. They got a paper published, and if anyone ever finds a tachyon or figures out how to detect them, the person will be hailed as a genius. But until then, He could be a crackpot, he could be a genius, I don't know. As with probably most theoretical things, when you're first presented with it, 99% chance it's pure crap, 1% chance it's brilliance. If it's that, even if it's that much. So right there, two things that I suspect that you grew up with, the fact that time seemed to be the same for everybody, and the fact that, two things happen at the same time for one person, they happen at the same time for everybody. Is there anything that's the same? Regardless of the reference frame? I mean, even in the muons, they agreed when the muon was traveling to the ground, from our point of view, the muons are traveling near the speed of light. From the muon's point of view, the ground was traveling near the speed of light. At least there was some agreement that something was traveling near the speed of light, but they disagreed on what. Well, there are actually two things that are the same. Speed of light, and we're assuming in a vacuum. So the speed of light is the same for everyone, regardless of how fast you're traveling, which definitely is completely against Galilean relativity. And let us go back to our thought experiment. Not that one, the one where we started. Got my lab frame, I got my box here, it's traveling at some speed v. I got the mirror. It's gonna shine the light up because there's a horizontal component. The light will be traveling like this and then come back and hit the box. This distance here is h. I know that the speed of light is distance, the speed is distance over time. And the distance it's going to travel, well, let's see, that distance there would be Vt. And so the distance the light's actually going to travel, this would be the square root of 1/2 Vt squared plus h squared. So the distance traveled would be 2 times the square root of h squared plus 1/4 v squared t squared over time. Multiply both sides by t, so I have ct equals 2 times the square root of h squared plus 1/4 v squared t squared. And now I'm going to divide by 2 and square both sides, so I get 1/4 c squared t squared equals 4 times h squared plus 1/4 v squared t squared, and that 4 should not be there because I divided by the 2 already. H squared plus 1/4 v squared t squared. I'm going to isolate h. H squared is equal to 1/4 v squared t squared minus 1/4 c squared t squared. To put this into, I'm going to multiply both sides by -4, just to put it in more traditional form. So I have -4 h squared equals c squared t squared minus v squared t squared. Now this v squared t squared, and I probably could have done this in fewer steps, but the v squared t squared is just the square of vt, which is how far the thing traveled. So c squared t squared minus x squared is equal to this. H is how far the box is from the mirror, the top of the box is to the mirror. If the box were traveling at a different speed, H is still the same. If we think back to when we were deriving the time dilation equation, H was the same in both reference frames. So it doesn't really matter how fast the object is traveling horizontally, that vertical distance is the same. So this is just some constant. In essence, we have c squared times how much time took place, and I'll put in the delta t at this point. This relationship between time and position is a constant. That is the same for everybody. To give it an analogy, doesn't exactly translate, but I think it will enough to present. If I have two events happening, different times in different positions. So this is my time axis, and this is my position axis. So I have two events that are happening, and I can figure out the length of that by just doing Pythagorean theorem. If my axis changes, the distance between these two dots doesn't change just because I'm changing my axis. And that's an analogy of what's going on there. Now, if we were truly doing the Pythagorean theorem, there'd be a plus sign. Just accept the fact that that should be a minus sign. This is just a different way of looking at it. Obviously, this is not a proof. All right, questions up to here? So we now have our second thing that is the same no matter how fast you're traveling. C squared delta t squared minus x squared. Right, so when I was in grad school, they had this, basically it was 3 items every week of breakthroughs in physics. Or at least whatever the editor felt were the biggest stories in physics. Ben Stein actually was the person who produced it, not the actor, Ben Stein. If you don't know who the actor Ben Stein is, if you've seen Ferris Bueller's Day Off, Bueller, B-O-O-D, that's Ben Stein, not the physics Ben Stein. So, while I was in grad school, one of the stories was they managed to get the speed of light down to about 6 meters a second. So how does that jive with the fact that speed of light is really closer to 300 million meters a second? What does it mean when you say the speed of light is slower than the speed of light? Well, how do you measure speed? Distance divided by time. So if I'm shining light, I have a block here, and I shine a light through it, and I figure out the time at which it enters, and I figure out the time at which it ends. I measure that distance, and I divide by the amount of time it took. That's how I get speed. So as it enters this block, the light is not traveling really in this straight path. And most of it is probably going to come out right here. But what light does is it hits an atom, gets absorbed, and then gets re-emitted. And then it will hit another atom, get absorbed, and then get re-emitted. And so light is going to basically, it takes time to get absorbed and then re-emitted, absorbed, re-emitted. So even though light is still traveling at the speed of light, there is an interference here that as light gets absorbed and then re-emitted. So what's really, so in between absorption and re-emission is traveling at the famous speed of light. But when they talk about how fast it's traveling, they are taking into account that amount of time. And so they have gotten the speed of light down to a very small amount. In optics, this is known as the index of refraction. Most of you have experienced some aspect of index of refraction, I assume. Pencil in a glass of water, and you see how the pencil's bent. That's because the light is traveling at a different net speed through air than it is through the water. And now know what you're thinking. You're going, hey, this is great, but okay, this is constant for this expression is constant. How can I actually translate between the two? Or more specifically, if I've got a 10-foot car, how fast do I need to be going to fit it inside an 8-foot garage? Let's find out. I'm going to do it the quick and dirty way, and then we'll get into a little bit more depth. And I want that car to be completely inside that garage. So here's the quick and dirty way. I know I'm not going to think about what's the proper frame, what is or is not the proper frame. This is the quick and dirty. I know gamma's got to show up in it somewhere.